about the image processing aspects of electron microscopy. So all the data analysis that we will see in these days are very much based in image processing. So let's see a little bit of the basic operations that we can perform with images, and let's try to understand them. If you have any questions at any moment, just stop me. So what we'll see is what is an image and how to code an image, what is sampling, what are the basic operations we can do with images, and a very fundamental operation that is the Fourier transform and trying. So an image is simply a variation of some feature over space. So for instance, we have this image here. So for each point in the space, we have a color, and all the colors together make a picture. So this is an analog picture. So you see a painting, it looks like that. If you want to put that into a computer, you have to discretize the analog picture. So you have to make small squares. These small squares, they are called pixels, and each pixel has a color. But since we are working with a finite machine, we cannot have absolutely all colors that are in nature. We have to quantize them. So we have bits. So you encode your image with a number of bits. So normally, if you want to encode colors, so we are all related to this RGB code. So RGB code is the sum of three lights, red, green, and blue. So you encode like this. For instance, let's say we want to represent red color. So you say red is the maximum number you can have. For instance, with 8 bits, the maximum number is 255. So you set 5, and the other two green and blue lights, you set them to 0. So you have red, pure red. So let's say you want to encode blue, so you do the same. You put red and green to 0, and then blue you put it to the maximum. So let's say you want to encode green. So this green color, in particular this green, it has red 0, blue 0, but it is not as greenish as it could be. It is not the maximum greenish value that you can have. So you put it to 1/2 of 255. If you want to create mixed colors, so you set, for instance, red to the maximum, green to the maximum, what you have is the maximum yellow that you can have with your representation. So if you use 8 bits, this would be the coding that you would have for your images. The kind of images that we use in electron microscopy, they are grayscale images. So that means that we have to encode gray values using this RGB. And there is a particular feature that is, if you want to get a gray color, all you have to do is to put the 3 values to the same value. Okay, so if you want to get white, you put 255, 255, 255. If you want to get black, you put 0, 0, 0. If you want any gray value in between, you put 128, 128, 128. So you don't have to write the 3 numbers. You simply need to write one number. So with one number, you have a gray color. So for instance, if you have the picture of this girl, you zoom it out and you see the pixels, and in the pixels you put, for each gray value here, you put the number that represents that gray value. So for instance, black values are related to small numbers. So all this area here of small numbers are representing this part of the eye. And then white values are more related to high values. So in fact, if you look from far, you can see the eye in these numbers there. Okay? So for an image, for us, will be a matrix of numbers. So now that you have encoded your image as a matrix of numbers, you can do a lot of operations with numbers. So let's see, for instance, what is the effect of the bit depth, how many bits you are using. Okay, so may I take the mouse, feel more comfortable, sorry. So I have a demo here where you have 2 images, one with 256 values, so 8 bits, and one with 7 bits. So the maximum number of gray values you can have is 128. And I cannot see any difference or visible difference between these two. So it means that the last bit is not adding much information to the image. And in fact, you can reduce the number of bits. You can go to 6, and I cannot still see any difference. You can go to 5, and you don't see much. Now you start to see with 4 images, with 4 bits. Okay, so with 4 bits you start to notice differences. But otherwise, you don't see much. So it means that we don't need so many bits to represent your images. In fact, in electron microscopy, normally we work between 8 and 16 bits. So depending on the camera, CCD camera, or the scanner for films, so we are working between 8 and 12. So I would say we have more than enough information to represent our variations in gray values. So we have been talking about the number of bits. So now the sampling. So how wide are our pixels? So how large we can choose our pixels, and we are not still missing any information. So here you have a pattern that is normally used to characterize optical systems, and this pattern, it has bars that are final and final. So here they are relatively coarse, and then they become final. There is a point at which you don't see the bars anymore. That is the optical resolution limit. So this is, you can imagine you construct this in reality. So you have all these bars, and now you take an image. And the thing is that this image can be represented. Sorry, this is not what I want. This image can be, these bars, here they are radially symmetric, here you have the same bars but vertically. So if you zoom out these bars, what you see is that you can think of these bars as a sine wave. Okay, so where you have a black bar, you would have a low value of your sine, and when you have a white value, you would have a high value of your sine. So you may think of these bars as going down and up, down all the time. Okay, so you have a sine wave there, and now what we are trying to figure out is how separated I can put samples on this continuous sine wave, so that I can put that into the computer. So I discretize my image. So if I put a lot of points, like in here, I can recover back the original sign. If I put too few points, probably I cannot recover the original sign. So that means here you have not lost any information, there you have lost some information. So let's try to see how this sampling is affecting okay, so here we have a certain here something like 1000. Okay, so we have a sine wave, and we are putting a lot of samples. At each sample, we would have a pixel. Okay, so we have many pixels to represent these variations of the white bars and black bars. So from these samples, we can readily recognize what is the sine frequency that we have there. So let's say that we increase the number of waves that we have in the same plot. So now we have a finer wave, so it changes more rapidly. So we have closer bars, and we can still see, well, here we have maximum, 0, minimum, 0, maximum. So we can recover what is the frequency of the sine. Let's say we keep on increasing. So now it is more difficult to see what is the underlying frequency, but there is a theory saying still you are in the same area, so you have not lost any information. You can recover the original sine wave. And this theorem is the Nyquist theorem. Now that we will break the Nyquist theorem, so we will load some information. You see that there is a very fine sine wave that is changing a lot, and however, from our samples, we would think that there is a sine wave that is much slower. Okay? So that is actually what is happening in our bars when we don't see them anymore. So there, what we are losing is the information of what is the frequency that is underneath. Okay? And that is called aliasing. So if you put fewer pixels than what you need to recover your information, you have lost information and you are beyond, you have broken the Nyquist theorem. Okay, so is it important? Well, we are dealing with molecules and we would like to see atoms, for instance, at this resolution, 1.2 angstrom resolution. So we see individual atoms there. So here we have an aromatic ring. And if your resolution, the maximum number of pixels that you can recover is 2 angstroms, you no longer see the individual atoms. And if you are worse, 3 angstroms resolution, you cannot distinguish at all what is inside. So even you cannot distinguish the hole in between here. So as a general rule, if you want to achieve a resolution, let's say of R, and for instance 4 angstroms resolution, your sampling rate, so the distance between one pixel and the next, has to be at least 2 angstroms per pixel. It can be better. So you can sample at 1.5, 1 angstrom per pixel, but you cannot sample at 2.1, okay? Because you would never reach the resolution of 4 angstroms. Okay? We have lost information to recover the original structure. This is Nyquist. So Nyquist say at most you can have 2 angstroms. In practice, it is recommended to have, instead of R over 2, it is recommended to have R over 3. So you are a little bit not to the limit. So the maximum sampling rate you would have for a 4 angstrom resolution structure would be 1.6 angstroms. If you have a sampling rate that is larger than that, you can never recover the 4 angstrom resolution. You know you have aliasing. Okay, so now we have an image in the computer. So what can we do with that image in the computer? So we can do many operations. So remember that an image is nothing more than a matrix of numbers. So we can do many operations with the numbers. So for instance, let's say we have an image representing this girl, another image representing this girl, and I can do weighted sums like this. So I can put 75% of this girl plus 25% of this one. Okay, so you take all the numbers, you multiply the first number of one image, so the pixel there in the corner by 0.25, the same pixel in the other image by 0.25, and you add the two values. And this would be the result. So mostly what you see is the first girl. And if you do the same with the second one, so now you put the 75% on the second image, so mostly what you see is the other one, and you see faintly this is Lena, this is Barbara, so you see faintly Lena there, and you may put 50%, 50%, so you can play with the numbers, and this is just for fun. In electron microscopy, we can do many more things than just for fun. So you can take many images like this. They have a lot of noise. Noise in electron microscopy normally comes either from the shot, from the Poisson nature of the electrons, from the recording device, from the eyes, mostly it is from the eyes. So you have your structure embedded in a lot of noise. And now you do the same operation that we did with Lena and Barbara, and now with your experimental images. And now the weights will be 1 over 1,000 because we have 1,000 images. So now, when you compute this average of all these images, what you see is the structure that comes out from the noise. Okay? So the noise cancels out, and the structure that is stable over all the experimental images comes out. Okay? So here we have Lena with a lot of noise, and you don't see any individual image, you don't see anything, but if you are able to average, and this averaging is just this operation, so you put a weight on each one of the images and you sum over all images, then the structure comes out because the noise cancels. So this is basically the essential of electron microscopy. So you take a lot of images with noise and then you average them into a 3D structure. So it is the main idea behind. The mathematics are more complicated, but the idea is this one. So we can also do operations at the image level. So for instance, here you have an example of some viruses. So these are the individual experimental images. So you barely see anything. But now, if you take images that look the same, so for instance, let's say these 3 images correspond to the same structure. Now you average them, what you have is this, what is called class average. Okay, so the class averages are nothing more than the average of the experimental images. So, and this classification that will be explained tomorrow by Jose Miguel, what it is doing is all these images look the same, so I put them into the same class. All these images look the same, I put them into the same class, and then I compute the class average for all those images. Then you can also do operations at the pixel level. Okay, so let's say that you have this picture into the computer, so every color there, it has an associated number, and now you count all the numbers. So how many times the number 200 appears? So you put 200, it appears 100 times, so you write there 100. How many times the number 200 once appeared? So now it appears 105 times. So you annotate how many times all the gray values appear. What you have built is called a histogram of your image, and it is an approximation of the probability density function of a random variable that represents your image. So this is a lot of work to do, counting all the pixel values, but you can do very nice things with it. So for instance, let's say you have this image, and this is the associated probability density function, this histogram that we have calculated before. And now there is a way of correcting the gray values in this image according to the integral of this probability density function. This is the integral of that function. So how to use this is, for instance, let's say you have a value 200 in the original image. So you go for the value 200, and now you look at by which value you have to substitute. So I have to substitute 200 by this number, and I have to substitute 250 by this number. Okay? So after the substitution, this is what you get. And this image has a nicer contrast than what you had before. So for instance, these clouds there, they were barely visible because the contrast between the cloud and the sky was very low, but now the contrast is higher. And this is due to this quick step there. So this is called histogram normalization or histogram equalization. This is one of the operations you can do. Here we can have a demo. So for instance, let's work with grayscale only. So let's say we have this image, and now you may change the contrast. This is the function that you are changing. So given the input pixel value, you substitute by an output pixel value. And you see how by changing this function, you're actually changing the contrast, and you can see better or worse your image. So let's go back. So we do also this for electron microscopy. So for instance, we are changing the input pixel values by the output pixel values, so that from this micrograph you can have this one. And you can see in this one, you can see better where your particles are. For instance, here there is a particle, you don't see it too well, you can see a little bit better. So it is not a magic, so not automatically shows all your particles in there, but it helps quite a lot to equalize the histogram or to do this histogram stretching. This is called histogram stretching because it is still a line, but it is not a line going from this corner to this corner. Okay, so If it is a line, it is called stretching. And we do this, this is one of the options that normally all the software packages have when you are picking particles, so this stretching or contrast enhancement, or they have different names for this. Also, let's say that you have collected your particles from your values, and there are certainly quite differences between, a lot of differences between these two images, and they should have more or less the same gray values because they correspond to the same structure. So why the gray values here are so white and here they are so dark? So you can renormalize the gray values so that more or less they have the same features, statistical features. And this is called image normalization. After doing the normalization, more or less they all look the same. And this is an important step in the 3D reconstruction process. So if you're looking for a volume that is compatible with all your projection images, all the projection images, the numbers that you have there, have to be compatible with the volume. If you start changing the gray values in each one of the images, probably it is very unlikely that you find a volume that is compatible with all of them, because you have been arbitrarily changing the gray values. So when you do a 3D reconstruction, it is important to normalize all the images so that, for instance, in our case, we do that the eyes that is here, so this is your particle, and the surrounding, we assume that it is eyes. So we put the eyes to have zero mean and standard deviation of 1. There is no reason to think why the eyes around your particle should be different from one particle to the other. Okay. So, and this is another step that you will do during the practices tomorrow. Here you have this idea. So here you have your values. So inside the values, we don't know how the gray values are distributed, but outside that are it is presumed to be only eyes. What you have is eyes. We force it to be zero mean, the standard deviation 1. The zero mean is also something fundamental for the 3D reconstruction. There is no volume that is compatible with something having outside in the borders something that is not zero, it's zero mean. Okay? So that is a technical detail. And if you look at the probability density function of all these pixels here, normally they look as a Gaussian. So if they don't look as a Gaussian, maybe you have an incorrect structure. So we have done operations at the level of image, at the level of pixels, and we can do also operations at the level of groups of pixels. Okay, so let's say that here is my image. So here are the gray values in my image, and now I concentrate on a central pixel and the pixels around it. So this is called the neighborhood, and in this neighborhood, what I do is the following operation. I multiply the central pixel by 9, all the surrounding pixels by -1. So here you have the result. So 9 times 103 is 927, and then minus 106 is minus 106. So you have now all these. You sum all these numbers, and you have a single number that is 130. So you substitute 103 by 130, and you do the same for all the pixels in your image. So this is called a convolution. Okay? So this operation of taking a central pixel, all the neighborhood, and doing some operations like this, it is called a convolution, and it is a convolution of your image with a kernel. So this mask here is called the kernel. By changing the kernel, you can have different effects on the output image. So here, let's say another example of how to calculate the convolution. So for instance, let's say we have an image that is 5 times 5 pixels with these gray values, 81, 22, 80, and we want to convert this image with this kernel. So what we would do would be to multiply all these numbers. So 81 times 0, 22 times -1, 80 times 0, and you put the results there, and now you sum all the values. Okay, so you sum the values. It is minus 117, and you put it there. So the central pixel was this one, and you substitute the sum of all these numbers at the location of the original pixel. And now you move to the next pixel. And you move to there, and you do repeat the same. So you multiply the gray values by your numbers, sum all of them, and then you have 13, and substitute the central pixel by 13. And you could do the same for all of them. So this is the convolution, to the convolution. Now, what you see, and next talk of Javi's about this, you would like to have a perfect structure of your, a perfect image of your structure. You would like to have this, but in fact the electron microscope, what is giving you is this. So the electron microscope, what it's doing is taking the perfect image of your structure and doing the 2D convolution with the point spread function. Here it is a funny point spread function, just for illustrations. So here it has 3 white bands, and the 3 white bands translate into these 3 shades there. Okay. But we have a point spread function that is kind of circular, and what we are doing is convolving this circular to the kernel with your ideal image. And by changing the kernel, so the convolution is not something bad necessarily. So if you play with the kernel, you can have nice results that may help you to understand better your image. For instance, here let's say this would be the ideal structure that we would like to see in the microscope. But the microscope, in fact, is convolving by this PSF, point spread function. It is giving something that is of lower resolution than the original image. So here, for instance, you see double stripes. Here you cannot see the double stripes. So you have lost this information. And the wider your point spread function, the worse it is. Now you have lost even more information. Let's go to the other extreme. Here you are losing a little bit less. So this is what is occurring in the microscope. But as I told you, if you change the mask by, for instance, computing this Laplacian, now you are able to detect edges in your image. So the convolution is not something bad. It occurs at the microscope, but you can also benefit from it by changing the mask to compute features of my image. So for instance, the Laplacian helps you to find the borders of your structure. This image is one collected by a telescope, and this is the sharpened version of this one, and this is just convolving with the right mask, with the right kernel. Okay, so you choose your kernel wisely, and you can go from this blurred image into a sharper image. So it is not you are inventing new information. The information was there, but you are highlighting it better. Okay? So this is also done in electron microscopy. Here we have an example in which we have a 3D structure, and now you convolve with something to sharpen your structure. So you have better details in this second volume than the details you have originally. And this is just done by sharpening. So we have chosen the kernel in such a way such that the information that was already there is highlighted. Okay? It is unhidden. You are boosting the high information, the high frequency information. We'll see later what is high frequency. Here we have another example. So you can use your kernels to sharpen information or to remove information. For instance, let's say that you have this micrograph. This micrograph has a lot of noise. Here we have big balls that are your virus particles. If you convolve with a smoothing kernel, so something that is blurring your image, what you have is a nicer image to the eye. So you prefer picking particles in this image, even if it has fewer information, but you don't care about all this information that is very noisy, so you don't care about the noise. All you care is about these high, big balls And these big balls are mostly low frequency information, so you concentrate where you want to recover your structure. Some interesting kernel is the following, and it is used in the correlation. So let's say that you have the habit of locating the eye of birds every time you see a picture of a bird. So I want to locate where the bird eye is. So what is the best kernel that is finding eyes in a picture of a bird? And the best kernel is an eye. Okay? So you take an eye of a bird, and now you convert your picture with your bird eye, and it will give, by this 2D convolution, it will give some numbers. The maximum number that you find in your output image is where the bird eye is. Okay? So you convert with this, and you look at the maximum value that is there. So the maximum value is actually locating where the bird eye is. And this is done, this is called correlation, and this is done, for instance, in many electron microscopy programs to find your particles. So you have a particle, how a virus particle should look like, and now you can convert your micrograph with your particle to find where the maxima are, and then all these maxima are giving you the locations of your particles. And this has a number of drawbacks. For instance, if you take the wrong structure to do this fitting, there can be a lot of model bias and so on. But if you do it properly, for instance, in XMIP, what we do is we construct this template from the particles you are picking, so you don't impose a model bias from an external structure, but from an internal structure. So then it is not so bad to do this picking. Also, what other kind of operations we can do with images? So we can do what they are called geometrical transformation. So let's say we have this image of Lena and we want to rotate it. So to rotate this image, what we would do is we have to put the numbers of this image in the output image. So what is the number that I should put there? So okay, so I compute where this pixel is coming from. So this pixel is coming from there. So I look what was the number there. It was 200, so I put 200 in the output image. And I do the same for all the pixels. And if you are doing a resizing of your image, if you resize your image, it is the same. So you have the original image, you want a smaller image. So all the numbers that you have to put in the smaller image, they are coming from the original one at a specific location. So for instance, here you look where it is 250, so you copy the 250 into the output image. So in principle, this is easy. In practice, when you compute where the pixel, what the pixel value is in the original image, it happens that because the transformation transforms coordinates in one image, in the output image into coordinates of the input image, it might happen that the coordinates in the input image are in the middle of nowhere. So you don't have the number for that pixel. So you would have to interpolate between the numbers you have around. Okay? So I have to copy the number from there, but I don't have any number there, so I look at the 4 numbers that are around my coordinate, and I produce some value out of those 4 numbers. And for instance, this might be a strategy. So you look at the 4 numbers that are around you, and somehow you fit a plane into those 4 numbers. There is a unique plane passing through these 4 values, and now you evaluate what is the plane value at the location where you are looking at. And this is called bilinear interpolation. But nothing prevents you. You have fit a surface to these 4 values. So you have fit a plane. So why don't you look at further values, at more coordinates, and now instead of fitting a plane, you fit a different surface. And a different surface, you can be as rich as you like. And for instance, you can reach fit a polynomial surface there, and this is called bicubic interpolation. And how you compute your values actually makes a difference between the quality of the output image. So let's say we go there. So here we have 2 images. Let me change this. So this linear B-spline is the bilinear interpolation that I told you before, so fit in a plane, and this is fit in a polynomial surface. So now what we'll do is we will rotate the two images by 30 degrees. So we rotate it by 30 degrees, and well, the two images more or less look the same. So in principle, it doesn't matter how you interpolate using bilinear or by fitting another kind of surface. Now we take the values in those two images, not the original values, and now we reinterpolate again. Now we rotate 30 degrees. We don't see much a difference either. But now we keep on doing this, and at the end, this image is much more blurry than this one. Okay? So how you interpolate your values really make a difference on how what is the final quality of your images. For instance, in next week, what we do is this one, this spline interpolation. It takes more time, so there is no free lunch. So interpolating like this takes more time than interpolating like this, but it is it has higher quality. And this is related also to an operation that is called downsampling. So downsampling is, let's say that you have a 10,000 micrograph, and you realize you don't have so much information, so you will never reach this 4 angstroms resolution. So you don't care reducing a little bit the sampling rate. So let's say you want to reduce the sampling rate by 2. So you have a pixel every 2 angstroms, and now you want to have a pixel every 4 angstroms. So one possible strategy is this. So I construct a super pixel that is bigger than my original pixels. Now the pixel size is 4 angstroms. The original one was 2 angstroms. So multiplying by 2, I have 4 angstrom pixel. And what is the value that I have to put in my output image? Is this the average of these 4 values? So this is one strategy. This strategy is called binning. If you want to multiply the pixel size by 4, okay, you do the same for 4 pixels. This has a limit that is always, you have to remind of 90. So the maximum resolution that you will reach is twice the sampling rate that you have in your new image. And doing this binning in this way, in fact, it can be proved, here we have a paper on that it is the worst way you can do it. There are much better ways of interpolating the output values of your images as a function of the gray values in your input images. And in fact, this also only do binning by integer numbers, so either be reduced by 2, by 3, by 4, by 5, but you cannot reduce by 2.1. And for instance, there are some other strategies that can do this 2.1 reduction. And this brings us to the Fourier transform. Okay, so the Fourier transform is a concept that is pretty much used in physics, in engineering. Probably most of you are already related to this or have heard at least of it. And it is related to how do we represent signals or waves as a sum of sine waves. Okay, so let's say that we have this signal, this square pulses, and we want to represent these square pulses as a sum of sines. So we would say, okay, so this function there is the sum of this sine, big sine, that more or less has the same separation between peaks. So the distance between this peak and this peak is the same as this one and this one. And since this sine alone cannot represent well the original signal, we add final sines. And the final sines, they have a property. This distance is called the period. So the period of the other sines are multiples or submultiples of the period of the original sine. So let's say this sine has a period t. So I have to add another sine of period t half, t over 3, t over 4, t over 5. These are called the harmonics of the original sine. So I have a fundamental sine and all its harmonics. So for all its harmonics and the fundamental sine, I have to compute what is the right amplitude and what is the right phase. So the phase, we will see it now, it controls when the sine is starting. If I control all that, by adding a few sines, I can approximate the original way. And the idea of the Fourier transform is that if you add infinite sines, in the limit you will recover exactly the original signal. So let's see all this in the demo. So this is how two sine waves are adding to construct a different signal. So if we change the wavelength or the frequency of the original signal, we see that larger wavelengths, they are associated to lower frequency, and it results in a function that is changing more slowly. So this is low frequency, this is high frequency, in the limit it changes a lot. And also you can control the amplitude, so you can make it larger or smaller, and you can control the phase. So you see that the phase controls where it starts, so you can move it to the left or to the right. And you could do the same with some other function, with some other way, and this is the sum of the two. Okay, so what we'll do is to construct a lot of sines like this, control the amplitude, control the phase, and control the frequency, and by adding all these sines, we will recover the original signal. So here you have an example. So we have a rectangular pulse, and we want to calculate what is the Fourier transform with just 10 sines. So we take 10 sines, and here in this plot we are representing what is the amplitude. So we represent the amplitude with this bar. So the larger the bar, the larger the amplitude, and the phase that we represent in here. So the phase is where the function is starting. So for 10 coefficients, we see that we approximate the original signal like this, and then we can keep adding more and more sines, and the more sines you have to add, the better you approximate the outcome. And we can see it also with something like this, for instance. So if you keep removing sines, you are approximating worse and worse your original signal. You see? So this is for 1D signals. So what is a sine in 2D? Because a sine in 1D, we are all related to them. So what is a sine in 2D? So here we have a nice representation of what a sine means in 2D. So let's keep it like this. So here what we have is a sine in one direction. So white values represent high values of your sine, black values, low values of your sine. So if you traverse like this, it would be down, and then up, then down, then up. So you are following the sine into D. And this is a vertical sine. We can do an horizontal sine, and the 2D sine, in fact, is the multiplication of the two. So this is how a 2D sine looks like. Okay, so it is the multiplication of a horizontal sine and then a vertical sine. It looks like this, and by controlling the frequency, what you are doing is controlling how wide all these cells are. So what we are saying is that we are going to decompose any image as a sum of this kind of images, in which we control the amplitude, so that means how intense they are, and the phase. And the phase means how we shift it to the left, to the right, to top and down. So we are decomposing all our images as a sum of this kind of images. So this is a 2D design, and here we have an example of how to decompose the image of this house into a sum of 2D signs. So here I'm only representing the amplitude and not the phase. So that would mean to recover this image, this original house, you would have to add a sign of zero frequency. The 2D Fourier transform normally is represented like this. Low frequencies are in the middle, and then high frequencies are to the extreme. So these are horizontal high frequency, this is vertical high frequency. So if you want to represent this house, you would have, you see here we have the wall of the house has a vertical sign that is very prominent. That means that we need a large amplitude for vertical signs. So these values, the signs at that frequency, at those frequencies, need high intensity. Then we also have, for instance, this diagonal sign. The diagonal sign is represented in diagonal. So this would be this intensity here, this intensity here. They are representing this diagonal roof of the house. And what is the harmonics now? So the harmonics are, this would be the fundamental frequency, and multiples of it would be the harmonics. So this would be the harmonic of this one, and along the same line you would have, this is second harmonic, third harmonic, fourth harmonic, so on. Okay, so now what we have there is what is the intensity to represent the house. So if you see signs in your house, you can identify what are the intensities at this 2D Fourier transform plot. But normally, standard images are not made of signs. They look like this. So, but the composition is general. So that means you will not see peaks in your Fourier transform. So we no longer see these high peaks in our Fourier transform, meaning that mainly what you need are these two waves, these two signs, but you see a continuous. So there is a continuous change from one frequency to the next. So you see a smooth function of the intensities. Normally, all the information for images are in the phases of the Fourier transform. It is not in the intensity of the Fourier transform. In fact, you see these two images look very different, but the amplitudes, the intensities of the Fourier transform, they don't look so different. And there is this interesting experiment. So let's say you take the image of a duck, you compute the Fourier transform. Here it is encoded the amplitude with the intensity, and the color encodes the phase. Now you do the same with the cat. So you take your cat, do the Fourier transform. Here again you have intensities and phases, and you construct an artificial Fourier transform. That is, you take the amplitudes of this duck and you take the phases of the cat. And now you combine all these numbers and do the inverse Fourier transform. And what you recover is a cat that is a little bit flat. It's some artifacts. So mostly the information of what an image is in the phase. Okay, so phases are very important for images. So now in Fourier space, what we can do is to put filters. And for instance, here you have an image. So it is an image of, let's say, some texture. And we want to identify, we want to separate some low changing component. Low changing component, you may see here, it is dark, and then white, and then dark, and then white. But we have only two periods there. So this is very low frequency. So this low frequency maps into the origin of the Fourier transform. So now we will put a filter that filters out the origin. So the origin will be multiplied by a value that is very close to zero. It is in the whole of this function. And then all the values in this ring will be multiplied by values close to 1. So when we multiply the Fourier transform of our image with this function, what the center disappears, and then what is in the ring stays. We now do the inverse Fourier transform, and this is what we recover. So what we have recovered are the signs that are whose frequencies are in this region. So those are those signs, and if you compute the difference between what you have recovered and your original image, what you have basically is the middle and the high frequency, but the high frequency normally you don't see so well. So here, by multiplying the Fourier transform by these kind of functions, what you can recover is you can separate low frequency components, so things that are varying very slowly, from things that are varying at a frequency that you are interested in. So you can separate the textures in your image. This is one strategy. The other strategy is this one. So in this strategy, you do the Fourier transform. Now you multiply by 0 all those values that are below a threshold. So you look at the intensities, all those intensities that are very rather small, you set them directly to 0. And you do the inverse Fourier transform. Now from this image, what you recover is this, and the difference with the original one is this noise image. So this would be a strategy to denoise your image. So let's see an example. So let's say we have this image and it has filtered by some sign, you see it there. So now we want to get rid of that sign. So let's say that I draw here, that sign is located in there, and probably it is also this one. So the more filters you add, you see I have virtually removed all these signs in the background. You see? So by blocking some frequencies, I can remove interferences. And this is removing some region of space because I have an interference. I may remove noise like this. So let's do it. So now I have a low pass filter whose frequency is this one. Kind of frequency. So let's keep it like that. Basically, it doesn't change. Now we keep on removing information. You see, I have removed all these the fine details. These fine details in the disk, they have disappeared because they are in this disk. You see? And now I'm going to remove the interference. We have removed the interference. Okay? So by low pass filtering, what you are doing is removing some regions of the Fourier space that you don't care. You can do exactly the opposite. So now you can remove the center. If you remove the center, what you are keeping are the high frequency components, so the part of the images that are varying very quickly. So this disk has a higher frequency variation than the original this part there. So by choosing the right region in the Fourier space, you can choose the information that you want from your structure. And this is another example. This is a bandpass filter. So here in the demo, what we have seen is low pass filtering removes high frequency component. High pass filtering removes low frequency components. But we can do both things at the same time. And both things at the same time would be a little bit like this. So you take the original image, you compute the Fourier spectrum, now you remove low frequency and high frequency components, and then you filter, you do the inverse Fourier transform, and this is what you get. Here in this example, you don't see much difference. Let's see an example where we can see it more better. So let's say, So we have this image. Now we compute the Fourier transform. Okay. This is just the amplitude. Now we do a bandpass filter that, and we compute the inverse Fourier transform. So whatever remains in this area, you do the inverse Fourier transform and we don't see much. So let's see if we can control it a little bit better what we want. So now I increase the area that I will keep. Now you see better. And you can, so remind, this is low frequency, so by moving the ring towards the center, we are adding more and more low frequency information, slowly varying information. So that is why the gel appears, because most of the gel is low frequency, it's very smooth, something changing with very smooth waves. We can add more. Now we cover more and more. And by removing high frequency, you see, we have removed the details. Okay? So the high frequency, what is related is to details, low frequency is related to the general structure, the general shape of your image. So by controlling which frequencies you want to pass, you can choose what to keep in your image and what not to keep. And for instance, in electron crystallography, one typical way of filtering images is like this. So you have your original crystal. If you look at the image of the crystal itself, you barely see anything. You compute the Fourier transform, now you see peaks. So all these peaks reminds of the house. So that the crystal is made of signs that are very well defined. It is not like the Fourier transform of Lena, where we have a continuous. So now we have peaks. So these peaks, now we may design a filter that is where your spots, these are called spots. So where your spots are. And now you filter out all the rest. And what happens is that now this image, if you do the inverse Fourier transform, you recover a crystal where you see the unit cell. And here I take the opportunity to introduce this concept of frequency. So the frequency that is measured in Fourier space as how far you are from the middle. So the origin has zero frequency. The farther you are, the higher the frequency. So the frequency is called F, and in continuous frequency it is measured in angstroms, 1 over angstrom. And this is related to 1 over the resolution, the Lutz term that we use normally in the electron microscopic field of resolution that we measure in angstroms. So you say I have a structure of 4 angstrom resolution, 10 angstrom resolution. In fact, in Fourier space, what you mean is that you have information up to 1 over 10, 1 over 4 frequency. Okay? So here you would have information. Outside that circle, we would not have information. I would also like to introduce a concept that is the convolution in Fourier space. So we have introduced already convolution. So convolution for us was an operation that was done at the level of group of pixels. So we were doing it in real space. So we took the image, we saw the pixels, and then we made some convolution operation with it. Now, the convolution has an equivalent in Fourier space. So when you convolve in real space, what you are doing in real space, in Fourier space, is multiplying by a function. So when we were before multiplying by this function, in fact we were convolving with some other kernel. But we don't define the kernel explicitly in real space, we define it in Fourier space. So let's say you have an image, original ideally, that you get, that is this one. Now you convolve your image with the point spread function. This is what the microscope is doing. So it has a point spread function, it computes the convolution in real space, in Fourier space, the equivalent is the multiplication of the two Fourier transforms. So you take the Fourier transform of your ideal image, the Fourier transform of your PSF, you multiply it both, and what you get is the Fourier transform of your observed image. This is what the microscope would be returning you, and now you want to recover the original image. So one strategy would be, okay, so all I have to do is to solve in this equation for the Fourier transform of I. So I take this term, move it to the other side by dividing by it. And now I have the Fourier transform of my original image. Now I do the inverse Fourier transform and I should recover the original. This has some drawbacks, you have to be careful by not dividing by 0 or this thing, but this is doable, and in fact this is an example. Remember, this was the original image, this is what you get, so you only see the letters, you don't see many details in the star, and now you have many more details in the star and you can see the better the letters. It is not perfect, so this strategy is not perfect, you see, you have some artifacts around the letters, but still you see much better than you did before. So the convolution in Fourier space is the CTF restoration that Harry will be talking later. So conclusions from this short talk would be the quality of an image depends on the number of bits you are using to represent it and its sampling rate. And we know now how these two parameters are used in electron microscopy. So normally we have a sampling rate that is high enough, but you know what is for your sampling rate, you know what is your resolution limit, and normally we work with more bits than needed. And then an image is a matrix of numbers. So with this matrix of numbers, you can do many operations. So you can do operations at the level of the full image, like the one of adding, computing the average. You can do operations at the level of pixels, like the histogram equalization, histogram normalization. You can do at the level of groups of pixels, like the correlation and the convolution. You can do geometrical transformations, like resizing or rotating. Then you can do transformations. We have seen the Fourier transform, but there are many other transforms, Rayleigh transform, wavelet transform. And the Fourier transform is particularly one of the most important ones in our field because it is related to resolution, and we have seen, we will see during the course how important resolution is in all this business. So from my side, that's